Hello everyone, welcome you join today's live session. My name is Charles Kim. I am an application scientist of Park Systems Korea. Today live talk's title is Crosstalk-free Ferroelectric domain characterization via dual frequency resonance tracking PFM. And end of this webinar, I introduced our new AFM, the FX40, and then to help you understand about the PFM measurement, we'll prepare the live session by using that AFM system. Here is the content. The first, we're going to see what is the piezoelectricity. And the second is the talk about the piezoelectric force microscopy. There will be the basics to know what is the PFM, and after that I will introduce the three different PFM modes. The first one is the off resonance PFM. This is very conventional PFM technique, what we generally do so far. And the second one is the contact resonance PFM. And the last one is most accurate the PFM technique and today's main the application. And the name is the dual frequency resonance tracking PFM. And for the last session, I'm going to show you the AFM experiment on the FX40, our new AFM system. And I also combine with the 3D instrument lock-in amplifier to do the DFRT-PFM. So here, what is the PFM? The PFM is the piezoelectric force microscopy. This is a scanning probe microscopy technique, and it can utilize the piezoelectric effect of the material, and you can generate the contrast, and you can mapping that contrast of overall surface. So in this case, the sample, the candidate is the most popular. The PFM sample is the ferroelectric material. And the second one is a piezoelectric material. And for special case, you can use the polymers and the nitride compound, and also the biological material sometimes can get the PFM signal. And also for the special case, if you want to switching the domain of the ferroelectric material, then you can try the electrical domain modification or the lithography by using the PFM technique. So the piezoelectricity. The piezoelectricity means the electrical property from the external pressure. Then typically the piezo material has the generation of electricity when the mechanical pressure is applied on the sample. And also in the opposite direction, when you apply the electrical field to the sample, then piezoelectrical material has the physical size or the dimension deformation. And also some specific piezo material is the ferroelectricity. The ferroelectricity is the property of the electric polarization, and the ferroelectric material already has the electrical polarization inside, and that polarity can be affected by the external field. Sometimes you can switch the domain inside by using the external electrical field. So the piezoelectrical effect is, there are two different effects. The first one is the tension effect. The tension effect means when you apply the one directional bias on the sample, then sample increase the dimension, so it's expanded, so become larger in the physical dimension. And in other case, if you change the direction of the voltage, then the sample be compressed, so decrease the dimension of the sample size. So by using this kind of the phenomena, we can use the piezo sample as some things to make a mechanical movement. You know, in case of the AFM, we should move the sample and the tip very precisely with a nanometer scale. So if you're applying and if you can control the voltage to the piezo material, then that piezo material can make a nanometer scale movement by using the piezoelectric effect. And here is the schematic of the PFM. So to measure that the domain inside of the piezo material, the tip works as a top electrode. And we make some circuit, so make some electrical contact or another contact at the bottom of the sample. And then we need to apply the external voltage between tip and then sample surface, sample bottom. So in this case, for the PFM measurement, we use the AC voltage as a tip bias to increase the sensitivity, signal sensitivity. And once we apply the AC tip bias on the surface, then sample will be oscillate because of the piezoelectric effect. Then that oscillation make the cantilevers bending up and down. Then that bending will detect by the SL beam. As you know, in case of the AFM, we must use some laser-like some beam at the backside of the cantilever. Then that beam will recorded by the photo detector. So if the sample oscillate in the vertical direction, then that oscillation is directly go into the photo detector. Then finally we can measure that small signal. And after that, if you move the tip position along the sample surface, then you can measure very small the domain or the information of the piezoelectricity inside. So the bottom images are the PFM images. So the first image is the height image of the bismuth ferrite. There is no big difference, and you cannot distinguish where has the different domain or different polarization here. But in the vertical PFM amplitude signal, you can see some contrast of the signal, and somewhere you can see very clear edges. These edges means the domain, the boundary between the upside polarization and downside polarization. And from the vertical PFM phase, you can see the clearly differences between the bright part and the darker part. So bright part means somewhere has aligned, and the darker part means somewhere aligned in opposite direction. So let's see what's the meaning of the PFM signal. Because we applying the external field as this blue color of the AC bias, then sample will be oscillate up and down. Then because of that up and down, the cantilever will detect some up and down signal as this red color. Then we can compare such an area has high deflection, then make a larger amplitude signal, but somewhere has small deflection, that means small oscillation, then it gonna make the small amplitude signal. Then from that information, we can guess where has the strength of the domain and where has the less strength of the domain. And the second one is the PFM phase. The PFM phase is detecting the phase shift between the excitation signal which we apply on the sample and then the signal from the PSPD, the photo detector. So if you see that phase difference between applying and the detecting signal, then we can guess the polarization of that point. For example, if the domain is aligned upside, then for example at the time if we got the same phase between applying and the detector. But in the case of the downshift the domain, then the phase shift will be 90-degree difference. So the the differences will be the 180 between the upside and the downside. So then let's talk about the PFM modes. Earlier I said that there are 3 different PFM modes, and first one is the off resonance PFM. So this kind of PFM techniques, the mode is decided by the frequency what we need to apply to excitate the sample surface. So anyway, we need to apply the AC bias, then we must choose the frequency of that AC bias. So in the case of the off resonance PFM, we generally use the 10 kilohertz frequency. Generally, in our case, we use the 17 kilohertz. But if this graph is the frequency and the PFM amplitude, you can find that somewhere the amplitude signal is going higher and has some peak here. So like this, at some specific frequency, the PFM amplitude signal has very strength point. That means the PFM signal sensitivity will be increased. You can get much clearer PFM signal if you use this frequency as a AC voltage on the sample. So, and then how we know this frequency is where is this frequency is? This frequency will be decided by the cantilever's resonance frequency. So I will talk about this more detail in the next slide. Generally, the 70 kHz for the off resonance PFM is very far from this resonance. And this contact resonance is near about 6 times of the free resonance of the tip. The free resonance means the resonance frequency of the tip without any contact on the surface. When the tip is just hanging on the probe hand, that frequency generally we use that frequency for the non-contact mode. So that frequency, there is that frequency, and at the 6 times higher frequency is the contact resonance. So what frequency we will use is decided the mode of the PFM. If we use the 17 kHz, then that is the off resonance PFM. And if we use this contact resonance frequency, then that is the contact resonance PFM. So this is the example result of the Parkway FM. The first screen capture images got from the thermal tuning. You know, the thermal tuning is measuring the thermal oscillation of the cantilever in the air. You know, every material is oscillating by the thermal energy, and that oscillation is become larger at the free resonance frequency. So in this time, I used the multi-75 probe. That probe has the 75 kHz of resonance frequency. And as a real measurement, the free resonance of this probe has the 72.8 kHz of the resonance. So after approach to the sample surface, I sweep the AC frequency. And the AC frequency, as a result of the AC frequency, I can get the contact resonance, the peak, at the 423.3 kHz. So it's about the 6 times of the free resonance. So by using this peak, we can measure the contact resonance PFM. So there is the one example images of the bismuth ferrite. In this slide, I want to talk about the crosstalk, topography crosstalk. So as you can see, in the height image, you can find many holes here. This sample is not flat like, but has some holes, many holes. And from the PFM image, you can see very clear the domain boundary here. And here somewhere has small grain, somewhere is a big grain. And from the PFM phase signal, you can see somewhere is very bright, and somewhere is dark. So we can guess these two areas has opposite polarization, and these two areas has the different domain. But the problem is this kind of the signal, this kind of the some black and dark area is very matched with the height image. So when I draw the line profile here, you can see the very big hole at the right hand side. But at the same point, there is the PFM amplitude signal drop, and also at the PFM phase, you can see the signal drop. So this is, we say this is the topography crosstalk in the PFM signal. Then why there is the topography crosstalk? And what is the reason of the topography crosstalk? Is because the contact resonance is very sensitive depending on the surface condition. Condition means the roughness or the mechanical property, whatever. But previously we only got the contact resonance at the single position as a 420. But when we check the contact resonance in some specific position first here, then at the time the contact resonance was the 358. But I moved to inside of this area, then contact resonance decreased. And also if I move to another position, then it's increased again. But not even change the contact resonance frequency, but also the contact resonance amplitude is become changed like that. So if we got the contact resonance one time and measure whole surface with that single frequency, then because of the contact resonance shift, we cannot measure the uniform or the clear image. And that kind of changes is has very big dependency on the roughness or the mechanical property. So to solve this kind of problem, we make the dual frequency resonance taking PFM. So if I zoom in here near the contact resonance area, then firstly we measure the contact resonance frequency and give the AC bias at the same position. But for the DFRT, to know the shift of this frequency, for the DFRT, we make the two more sideband at the right and at the left position. So both has the same differences from the center of the resonance frequency, and the system will detect the ratio between sideband 1 and sideband 2. So for example, if the contact resonance shift to the left side, then left side sideband will increase and the right hand side the sideband will decrease. In this case, system immediately know the breaking of the ratio between sideband 1 and 2, then immediately move the AC frequency to get the same ratio between sideband 1 and sideband 2 like this. Then the new AC frequency is updated in real time and the system do the frequency feedback. So let's summarize. Then the frequency feedback is work as the compare the amplitude of the sidebands between 1 and 2 and adjust the frequency of AC excitation to keep the amplitude ratio of sideband constant. So there is the example images of off-resonance PFM, content resonance PFM, and DFRT-PFM. By using the off-resonance PFM, the signal is very weak and result is very bad. But by using the contact resonance PFM, we can measure a very clear image. But you can see some horizontal stripe. We can guess this is the crosstalk from the topographical information. But by using the DFRT-PFM, the DFRT amplitude is super clear and the phase as well. And there is no some contrast or stripe artifact. So this is the DFRT is most accurate the PFM signal compared to the content resonance and off resonance. So then how we can measure the PFM, and there is a sequence of the PFM measurement. It's very simple. The first we need to prepare the probe and the sample. And for today's live demo, I'm going to use the multi-75E and G probe. This probe has the 75 kHz of the resonance. And the sample will be the PMMPT. And the next step is the approach on the surface to get the contact resonance. And after that, we need to choose the frequency depending on the modes. So first, if you want to measure the off resonance PFM, then just you can use the 17 kHz of the AC bias. But if you want to use the contact resonance, then you can sweep the bias of the frequency to find the contact resonance. Then there will be about the 6 times frequency you can find the contact resonance. And if there is one more step for the DFRT is to find the contact resonance, and you need to generate the two more sideband near the contact resonance frequency. After that, if you do the frequency feedback, that is the DFRT-PFM. So the modes can provided by the FX40 system. But to do the DFRT-PFM, we need to combine with the 3D lock-in amplifier. So this is the hardware setup for the DFRT. You know the DFRT is use the external lock-in amplifier. We need to make some signal transport to this external lock-in amplifier. So the vertical information from the cantilever, it should go inside of the 3D lock-in amplifier. And when you do the just off resonance PFM or the content resonance PFM, you don't need to do this one. And the second one is the output signal from the lock-in amplifier. The lock-in amplifier must generate the AC signal to make electrical oscillation on the sample surface. So in case of the DFRT, we need to connect the cantilever to the lock-in amplifier or by the 3D instrument. But in case of the off resonance, you don't need connect any external bias because the AFM head already has the internal bias. But in case of the contact resonance PFM, we need to connect to the backside of our AFM controller. So these points are a little bit different depending on the modes. And the last one is the signal detecting. The 3D lock-in amplifier will calculate the signal differences between the external, the AC bias, and the vertical oscillation information from the cantilever. Then after that, the PFM signal calculation, then you can connect the 4 auxiliary outputs and the 5 auxiliary inputs between the lock-in and the AFM controller. And here, same, if you want to do the off resonance PFM or the content resonance PFM, you don't need connect any external signal because our AFM controller can do inside. So for the last of this presentation is quick overview of the FX40. The FX40 is very new AFM, and this AFM is focusing on the automation. So first automation is Autoprobe exchange. You know, for the AFM beginner, the tip exchange is very challenging. You can drop it or you can breaking before use it, so it's very hard. But in the FX40, there are up to 8 the area you can prepare the pre-aligned cantilever. Then AFM head can approach on that cantilever side and can pick up. And after use the cantilever, if we want to return at the Autoprobe exchanger, then AFM head can drop the cantilever on the Autoprobe exchanger. And not even the pickup and the parking, also the AFM system can read the QR code at the backside of the chip carrier. Then from this QR code, the AFM system recognizes the cantilever type and also resonance frequency and the force constant of the cantilever. And for last of the cantilever preparation, you know, because of AFM using the SLD beam, the laser beam, you must set on the backside of the cantilever, and also you need to align to the photodetector. So there are 2 alignment steps, but that all the 2 alignment steps will be done by automatically in the FX40. And not only special in the probe, but also the sample loading has some special function. First is you can load up to the 4 different samples, and there are the hole at the sample disk. So you can put the sample and you can return the sample as at the same position. If we want to use it again, if we want to measure it again, even you detach the sample and attach it again, you can get the same sample position. And there's one camera upside of the sample stage. The total 4 different samples can capture as one single image. Not only the capture it, and also you can move this point to the somewhere if you want to measure, and move it and click the go to button, then system will go the position directly. Then just you need approach on the surface. And this is the summary of the presentation. The PAC systems provide the various PFM mode. The first one is off resonance. The off resonance can measure the high piezo response sample, but the sensitivity is low, so there is no crosstalk from the topography. But the off resonance is good for the high piezo sample. So in case of the weak piezo response sample, we need to use the contact resonance PFM. But the contact resonance is changing depending on the surface morphology. So it's only good at the low roughness surface sample. So to solve this kind of problem, the DFRT-PFM is good option. The DFRT-PFM is the most accurate and crosstalk-free PFM, and even the weak piezo response sample, it gonna measure the very high signal contrast. And all the mode is available on the PAC systems, FX40, and even the NX research AFM is possible to do. And to do the DFRT-PFM, it will be available with combining the 3D locking amplifier. So this photo is the 3D locking amplifier, and this locking amplifier can combine with the NX Research AFM and our new FX40 system. So let's finish this presentation, and I will show you the real PFM measurement. Okay, this is the Smart Scan. The Smart Scan is a AFM control software. And please have a look at the right hand side. This is the internal camera of the acoustic enclosure for the FX40. You can see the FX40, how it moves and how it detects is by this camera. I said in the previous presentation, the FX40 is focused on the automation, and there are the two biggest automatic parts. The first one is the probe, and second one is the sample. Let's have a look at the probe first. When I click the probe, there is one camera on top here, at the right side. And now nothing is updated here. So let me click the unload to put the cassette inside. When I click the unload, the ATX door is open and is ready to put the cassette. The cassette means this is a probe cassette. There are 8 different cantilevers, and I can put this one on the system. And after that, release the top cover and remove it. After that, click the load button. Then ATX go inside. And let me click the detect to detect the QR code. Then, as you can see, there are the 8 different slots, and it's updated what cantilevers is located at each slot. And the second one is the sample. Let me click the sample and click the unload. Then left hand side camera is open, is working, and it's capture the sample surface. And let me put the sample inside. After put the sample inside, click the load button. Then the capture image is updated. After that, you can move the point. Then you can save this position here. For example, if you have 4 different samples, you can save each position like that. For this webinar, I just used a single sample here. Then, for the PFM measurement, let me pick up the sample from the Autoprobe exchanger, and after that, I will move to the scanning position by using the sample. Let me click the pick up at to pick the probe. When I click the pick up button, then AFM head goes down to pick the probe. Then probe is jump up to the probe end of the AFM head. After that, by using the machine learning, the AFM system find the exact probe position. And after that, move the AFM probe at the center of the vision and align the beam automatically. Then the user don't need to do it manually. Just click the single button, then probe preparation is done. And after that, click the sample, and let's move to this sample position. Click the go to button. Then XY stage move. Then the sample located under the tip. Let's approach. Goes down the probe near the sample. Let me connect the external bias wire. Okay, let me approach again. So, for the first step, I will try the off resonance PFM first. Another name of off resonance PFM is the AM PFM, and the AM means the amplitude modulation. So, because of this off resonance PFM setup, so the contact resonance sweep button is disabled now. So, just click the lock-in amplifier. Then, as you can see, now the setting is the 17 kHz. And the driving the voltage is only 1 volt. Start the line scan. Then the G height signal is updated here, and amplitude and the phase is got. But as you can see, there is no some special signal. So let me increase the driving voltage. As you can see, there are little differences, but still the signal is very weak. So let me increase to the maximum. So this is the AM, the signal. So let me scan quickly. So by using the off resonance PFM, we can measure this kind of signal of the PFM amplitude and the phase. But as you can see, the signal is very weak and noise. This is the G height signal, and this is the amplitude signal, and this is the phase signal. To save the time, let me stop the imaging and skip to the contact resonance PFM. To measure the contact resonance PFM, it's better to know the real resonance frequency of the probe. So let me increase a little bit the tip, and let's try the summer tune. The summer tune is detecting the summer oscillation of the tip. Then as a result, you can see the small peak here. So this peak is located at the resonance. The resonance of this probe is 72.8 kHz. So I said earlier, the contact resonance is obtained over the 6 times of this resonance frequency. So approach again. And click the contact resonance button. Then contact resonance sweep button will be able. Then click this one. And because we expect the contact resonance is come near the 400 kHz, let me start from the 300 to the 500. Click the start. Then you can see the biggest peak here. And in this time, the contact resonance is 433. Let me scan again. Then this is the contact resonance result. But now only the 1 volt the driving force, but previously in the off resonance there was no signal, but by using the contact resonance you can see the signal. And let me increase a little bit up to the 3 volt and start the measurement. Then compared to the previous image, the PFM amplitude signal is become a little bit clear, and phase signal also become less noise. This is the contact resonance PFM. To compare with the DFRT, so let me scan a little bit bigger. So let's compare the amplitude and the phase. The left one is the PFM amplitude and right one is the PFM phase. Actually this sample is quite flat, so there is no big topographical crosstalk. But anyway, let me use the DFRT as well. So please remember this, the value and the quality of this image. This is the contact resonance result. And then to perform the DFRT-PFM, we need to control the GD locking amplifier. So this is the GD locking amplifier. We need some extra software to control it. So you can see the sweeper. The sweeper means the sweep the resonance frequency. So it's same like previous. We need to sweep from 300 to the 500 kilohertz. And then click the single button, then it will perform the single sweep. Then there are updated the 3 different curves at the same time. But the resonance frequency is not so clear, so let me move a position a little bit. And click the button again. Then you can see, let me clear the previous one. Then you can see the peak at near the 420 kilohertz, and there is the 2 different sideband as a orange color and the green color. So these are the sideband. So to get the best result, it's better you get the full width half maximum of this resonance frequency. It's almost 7 kilohertz. Then put the half of the 7 here. And then let's start again. Then as you can see, even I sweep it again, but contact resonance frequency is shifted a little bit. And now it looks fine. The sideband are located at the right position and contact resonance peak is clear. And the next step is enable the feedback. The feedback means, I said before, because of the contact resonance is shift during the scanning, so it need to feedback. to tracking that shift. So click this button. And then jump to the smart scan. And because of the 3D locking amplifier is the external tool, we need to connect with the auxiliary connector. And aux2 and aux3 is connected with the 3D locking amplifier. So now the signal is not so clear. So let me change the driving voltage a little bit higher. Then you can see this is the DFRT-PFM. And in this time, if I see the aux4, this is supposed to be the frequency tracking result, but it's noisy, so let me check the what's the problem. Okay, previously we got the resonance frequency at the 433, so we need to update this value at the PID. And let's see again. Then you can see the real-time differences of the resonance frequency is it looks better than the previous noise. And let me scan it. So this is the DFRT image, but it seems not clear compared to the contact resonance. But that means we can guess the previous signal was from the some crosstalk of the sample surface. So as you can see, the phase signal is this. The aux2 signal is PFM amplitude, and aux3 is the PFM phase. Because of the time limitation of today, I want to show you some pre-measured image on the same sample. So this is the same sample's height image, surface morphology. And this is the contact resonance amplitude. And this is a contact resonance phase signal. And this is the DFRT amplitude signal. This is DFRT phase signal. So to see the better comparison, let me delete the height signal. So the upside one is the PFM signal by the contact resonance, and downside signal is from the DFRT-PFM. As you can see, the contact resonance PFM, it looks clear, but that means some of the signal is come from the height, the crosstalk, because the DFRT is get rid of the crosstalk from the topography. So we can believe this signal is only from the piezoelectrical domain inside of the sample surface. And let's finish this live measurement. And if you want to finish the measurement, then click the Pro button and just click the Pack Into. Then the FX40 return the probe on the probe exchanger. Then all the measurement is done. This is the end of today's webinar. Thank you for your attention. Please feel free to ask me if you have any questions or comment. Thank you.